Hi there, hope you're doing well. Welcome to the lecture on repeated measures ANOVA. Very exciting stuff. Now, you might see me refer to repeated measures ANOVA as RM ANOVA, so just wanted to give you a heads up. I just wanted to reduce the number of words you see on the screen. So if you see RM ANOVA, that means repeated measures ANOVA, which is our topic today. So first, we'll cover the conceptual information related to repeated measures ANOVA. For example, what is it and what does it do? Then we'll work together on a demo using the Psych 300 Data 2 dataset. And we'll cover some basic steps you want to run in our studio, and there are quite a few steps to think about, and then how to interpret your results. And then we'll go over a quick summary, and we'll be all done for today. So let's get started. So what is the repeated measures ANOVA? This is a form of an ANOVA when each case provides multiple measurements. So there are repeated measures of the same participant or case. So for example, each person or case completes all of the treatment conditions left, center, and right. So you might see that in cognitive studies. Or it provides multiple ratings, closeness to parents, partners, and friends. Or it's measured over time, so there are multiple measurement occasions of the same variable. And so you might remember a form like this in paired samples t-test where the means are related. And so now we're kind of looking at a paired samples t-test on steroids where you're comparing more than two means. So why should we use repeated measures ANOVA instead of a bunch of pairwise t-tests? Well, one advantage to using repeated measures ANOVA is that it reduces error variance due to individual variability, and so it takes it out. So if you remember the F statistic, it looks like this, where you're taking the ratio between mean squares between and mean squares error. And the verbal translation is like this, where the denominator is about the variance due to between group effects, and then the denominator is about variance due to within treatment or random differences or error. But this time you're actually subtracting from the denominator individual differences. And so again, the numerator is about the variance due to group differences. The denominator is about variance due to error. And then you're subtracting from the denominator variance attributed to individual differences. And so what that does is that denominator shrinks in repeated measures ANOVA because you're subtracting from the denominator the variance attributed to individual differences. And so, because the denominator is shrinking, the F statistic is going to get larger, and it provides a more powerful test of your hypothesis. And that's a pretty persuasive reason to use repeated measures ANOVA instead of a whole bunch of, let's say, paired samples t-test and whatnot. So this is the logic broken down into a diagram. And so stage 1 up here is the usual ANOVA, where the total variance is broken up into between group or between treatments variance. That's the numerator of the F ratio. And then the denominator is within treatments variance, or error. But in this case, there's stage 2, and you're taking out between subjects or between individuals variability. And so individual differences is taken out. And then you're looking at the remaining error variance as the denominator of the F ratio. And so, again, the F ratio is supposed to get a little bit bigger as a result and provides a more powerful test. And repeated measures ANOVA now has a new assumption. It's called sphericity. And sphericity says that there's equal variance among differences in scores between all levels of the factor. And so for example, if you take a difference between group A and B, then the variance of that is the same as the variance of the difference between groups B and C, as well as the variance of the difference between groups A and C, and so on. And so if you think about it, this might be easier to just kind of understand. So let's say that you have each subject measured in group A, group B, and group C, and then you take the difference in scores across those three groups pairwise. And then the variance for those difference scores should roughly be all equal. So these guys should be roughly equal. And so it's kind of like looking for homogeneity of variance, except for that now we're looking at the homogeneity of variance for the difference scores like this, as opposed to around the individual group means. Now there's a test that will allow you to check for sphericity, and that's called the Moschli's test. And the Moschli's test has a null hypothesis that says group variances that we just looked at are equal to one another, in which case the sphericity assumption is met. And so as you will see when we get to our studio, you will obtain the results of the Marshallese test within the same procedure as the repeated measures ANOVA you run. Now, just as a side caveat to tuck away at the back of your mind is that Marshallese test may underestimate problems in small samples and overestimate them in large ones. And so when you start looking at very small samples or very large samples, you want to just tuck this away at the back of your mind. That is just FYI. Now, the Marshallese test will look like this, very basic, in our studio. This is just sample output. And here is what's called Marshallese W. So that is the test statistic that will allow us to test for sphericity. We don't really pay attention to that as much as here, the p-value, because really with Marshallese test, very much like Levine's test, what we care about is whether or not the assumption is met. And so whether or not you reject the null hypothesis or not. And so essentially when you get the Marshallese test, look at the p-value, and then that will tell you what to do. And so in this case, the p-value is greater than 0.05, and so we would retain the null hypothesis, or fail to reject the null hypothesis, and so we can assume that there is sphericity, and there's nothing that you have to do. Hooray! So again, if the p-value is greater than alpha, then you retain the null hypothesis, and you have met the assumption of sphericity. And so you can carry on and do nothing extra with the output that appears underneath the Marshallese test in our studio. If you do get a significant result, so the p-value is less than 0.05, then you reject the null hypothesis. The assumption is not met, and so you would have to look at additional information underneath, which is something that looks like this, and it's labeled greenhouse geyser and Humboldt corrections. Now, what is this? And so what we're looking at here is the epsilon, which is abbreviated EPS in this output. And so they appear here for greenhouse geyser and for Humboldt. And the epsilon is actually the correction factor for your degrees of freedom for your F statistic, so the overall ANOVA test, in case sphericity cannot be assumed. So it's kind of an index of the degree of sphericity that you have, and it ranges between 0 and 1, and the closer to 1, the better. In this case, the epsilon is very high. So let's talk about the two types of epsilon that you see. The first is greenhouse geyser, abbreviated GG, and that is a more conservative epsilon, especially for small samples. The Humboldt, the second one, abbreviated HF, is a more liberal approach with epsilon. And you want to just kind of eyeball the epsilons that come up here for GG and HF, and think about whether or not the epsilons are greater than 0.75 or so. And so there's no hard and fast rule about which one to use. And so in general, the rough cutoff will be about 0.75. And so if you notice that the epsilon tends to be greater than 0.75, then I would use Humboldt. And then if you notice that epsilon tends to be lower than 0.75 and on the low side, then I would use the greenhouse geyser epsilon. Now, what do you use it for? What you would use it for actually is to apply this to the degrees of freedom for your F statistic. And so you would multiply the epsilon that you choose, greenhouse geyser or Humboldt, multiply that epsilon with both the numerator and the denominator degrees of freedom to get the correct adjusted degrees of freedom for your F statistic. And so I think a lot of this will make more sense when we actually go to our studio and take a look. But the main thing to remember is that when you see an epsilon, you would be using it only if Marshallese test comes up significant and you have not met the assumption of sphericity. Now, in which case you'd want to decide whether to use greenhouse geyser or Humboldt, and use that epsilon, multiply that with the numerator and the denominator degrees of freedom to get the adjusted degrees of freedom for your ANOVA. That was a mouthful. All right, so great job contemplating the conceptual information behind repeated measures ANOVA. Now we're going to go into the demo shortly, but go ahead and take a break and take a moment to answer some review questions, and then we'll resume right back up where we left off with our demo. See you shortly.